So many of you may have studied logarithms in your high school or your junior college, and some of you may have extensively used logarithms in your future education. But there would be many of you who studied logarithms for the sake of studying and then later wondered, why did we ever study logarithms? What is their use? In this video, I hope to be able to tell you that logarithms are not just mathematical concepts, but something deeply embedded inside all of us. So let's begin with a review of what logarithms are. So let's say that I have a quantity A, then I can also denote it as what we call A power 1. Now if I multiply A with itself, then I get a quantity which is, we call it A square, or A raised to the power of 2. Now suppose I do A into A, total of 3 times, then we have A raised to the power 3. So if A appears 3 times, then we have A cube. So similarly, we can make a general notation and we can write A into A x times, and that would be called A raised to the power of x. Now suppose I define the quantity y as A raised to the power of x, then logarithm is defined as follows. Logarithm is an operation which uses what is called as a base. In this case, the base will be A, and it will accept y as an input and give us x as the output. So what does logarithm really do? Well, a logarithm is an operation. It is done with respect to some base which is A, right? We supply it a quantity y, and the output of the logarithm is the x, where x is the value by which we should raise the power of A to get y. That's confusing. So let us go back to this equation here. So y is what I am providing as the input to the logarithm, and I am choosing a base A. The x that I am getting is a quantity such that I have to do A into A x times in order to get the y. Okay, so this is the summary of a logarithm again. It is an operation where we choose a base A, we input a quantity y, and we get in return what is the power by which A should be raised in order to get y. Now those of you who have studied logarithms in detail would have got a quick revision. For those who are looking at logarithms after a very long time, I would encourage you to pause the video and take a look at this slide in greater detail and just let the concept sink in. If not, we can move on. So let's look at some examples of logarithm operations. So log of 10 to the base 10, now base 10 is one of the most common bases that we choose, is 1. Similarly, log of 100 to the base 10 is 2, and log of 1000 to the base 10 is 3. Now let's understand why this is so. That's because 10 needs to be raised to a power of 1 in order to get back 10. And that is why log will give you 1, because log is supposed to tell you what is the value by which you must raise the base, the power of the base, in order to get the input. So how much do I need to raise the power of 10 in order to get 100? By 2, because 10 into 10 is 100. Similarly, 10 into 10 into 10, that is 10 cube, is 1000, and therefore log of 1000 is 3. Alright, so on the basis of our understanding of logarithms so far, we can now define something called linear responder and logarithmic responder. So let's see how that works. Suppose there is a signal, right? And the signal changes as follows. First it is 10 units, then it's 100 units, then it is 1000 units, then it is 10,000 units, and so on. Now what is that signal? It doesn't matter. It could be the amount of light something is receiving. It could be the amount of current in a circuit. It could be the amount of heat generated by an engine. It could be the amount of force generated by a human being pushing another human being. Doesn't matter. Just some signal. It is measured in some units, and we have 10 units, 100 units, 1000 units, etc. Now, a linear responder is the one which says that after receiving the signal that yes, it is 10, yes, it is 100, yes, it is 1000, and so on. So if I ask a linear responder, can you tell me how the signal is changing? Then it says, yes, initially the signal increased by 90, then the signal increased by 900, then the signal increased by 9000. However, if I take a logarithmic responder, it says the response 1, 2, 3, 4. Why? Because a logarithmic responder can only see the log of the value. So it sees log of 10, it says 1. It sees log of 100, it says 2. It sees log of 1000, it says 3. And if you ask a logarithmic responder, hey, how is the value changing? Then it says it is first increasing by 1. It is then again increasing by 1. And then it is again increasing by 1. So you see how the linear and logarithmic responder are very different from each other. One is noticing changes as differences. The other is seeing the change in the power. Okay. Now we need to deviate a little bit and go into a history lesson in astronomy. So let's see why I'm taking you through a history lesson in astronomy. We need to go back to ancient Greece, a few hundred BC. There was a gentleman by the name Hipparchus, and he constructed a catalog of 1000 stars. And what he did is, using only his eyes, because there were no telescopes or detectors back then, he said, I am going to call the brightest star as the first magnitude. Then I'm going to call the next brightest star as second magnitude, and so on. He went until sixth magnitude, and he compiled a catalog of brightness measurements for the stars. And this is how the measurement of brightness of stars is done, using magnitudes. So higher the magnitude, lower is the brightness, because it's like a rank. The lower the number, better is your rank. So it's first brightness, second brightness, and so on. Now several hundreds of years later, Paulson did the following experiment. This is a very loose version of the experiment. So imagine there are two stars. Okay. Now these are not two stars of different sizes. These are two stars of different brightnesses. Just for sake of drawing, I have taken the brightest star and drawn it as a bigger star. Now I have two telescopes, right? And they are of exactly the same diameter or area, whatever you want to, unit you want to use. Now, why is the area important? Because the total amount of light collected is different for telescopes of different sizes. So what is the difference between a bright object and a dim object? Well, the bright object, you are receiving more light on your eyes, and therefore it appears brighter. So similarly, a telescope is like a big eye, and if you have the eyes of the same size, they will see similarly. So when the light is allowed to pass through these two telescopes, we get the same picture, which is that one star is brighter than the other star. However, what Paulson did is that he took the telescope observing the brightest star, and he decided to cover it with a coating, so that the total amount of area which is collecting the light is lower. Now what happened is, the brightest star appeared to be as faint as the other star. And he was able to measure how the change in area is reducing the brightness. And he was able to come up with his famous equation, which is the cornerstone of all astronomical photometry, which is the Paulson Scale, where he says that m1 minus m2 is minus 2.5 log of f1 by f2, where m1, m2 are the magnitudes of the stars as defined by Hipparchus thousands of years ago, and f1 and f2 are the effective amount of light being received from the star on the telescope surface or even the eye's surface. Now, don't worry about the technicalities of this equation. All you should pay attention to is this log. And that tells you that your eyes are logarithmic responders. And you should be thankful that the eyes are logarithmic responders and not linear responders. Let's understand this through a simple example. Just before making this video, from the inside of my house, I took a photograph of a window. This is the photograph that I took. Now you can see that everything outside is visible, but inside everything has been darkened. In fact, the curtains have very good texture in them. On the left side, there is actually a chair which you cannot really make out. Well, my eyes could easily see the chair, the patterns on the curtains, but the camera is not able to capture this because according to the camera, the outside the window part is several hundred times brighter than the part inside the window. Whereas according to my eyes, which are logarithmic responders, the difference is not substantial, and therefore we are able to see both very bright and very dark places simultaneously, which is something the camera, a digital modern camera, cannot do so, which is why many cell phone manufacturers are now giving you HDR modes to compensate for this problem. HDR basically stands for high dynamic range. It increases the range of brightnesses that can be observed simultaneously. So there is another sense in our human body which is also logarithmic. So where else do you find logs inside yourself? Well, it is in your ears. Because if you see the equation for the unit of volume, so when you change the volume by what are called decibels, the equation that tells you how the power of the behind the sound production is changing is again a log equation. So our ears are also logarithmic responders. So in these old instruments where you had these beautiful volume knobs, you think you're changing the volume by 1, 2, 3, 4, but in reality, the signal's power is increasing something like 10, 100, 1000, 10,000 and so on. So that brings us to the end of this video, and the key message that I wanted to bring out here was that logarithms are not just mathematical constructs, they are in you. I hope you liked that video. I'll see you again soon. Thanks.